Hello students, in today's class, let us understand about the interference process in thin films. Interference in thin films is an example of interference by division of amplitude, as opposed to the Young's double slit experiment, which is an interference by division of wavefront. So here the incident beam will be splitted into two by reflection and refraction. So as you can see, this beam A that is falling onto the thin film. This is the thin film. The shaded region is the thin film made up of glass. Above this glass piece we have air here, and below this glass piece we have air. So this is a thin film of glass whose refractive index is mu, and when this incident ray falls on this thin film, a part of it will be refracted into the glass beam and another part will be reflected back into the air. So here at the point B, the incident beam is getting splitted into two. One is going out as ray 1 and the other part is getting refracted into the glass plate, and that part on reaching the point F will undergo reflection again and will be reflected back into the glass, and it will reach the point D. From there it will get refracted into the air. So the beam 1 that is coming in from the point A is getting splitted up into two. One is getting reflected from here as ray 1 and the other part is being refracted into the glass, from where it is reflected back and it is coming out as ray 2. So here ray 1 and ray 2 originates from the same incident beam. One takes a path like this. From A it reaches B and goes like this and reaches C, and the other takes a larger path, like it goes from A to B and then it goes inside and reach point F. From there it is getting reflected and reach D, and from there it goes up to E. And these two rays, ray 1 and ray 2, can give rise to an interference pattern. They can actually superimpose as per the superposition principle, and they can give out an interference pattern. When we study about the interference pattern by these waves, we actually have to look for the path difference delta, the optical path difference delta. So we would not be deriving this equation, but simply remember that in such a case of interference by division of amplitude from a thin film, we have the equation for delta to be equal to 2 mu t cos r minus lambda by 2. Here mu is the refractive index of the thin film, here it is glass. T is the thickness of this thin film, here it is T. How thick is the glass plate? Then R is the angle of refraction. Here this will be R, angle R. The incident beam will be refracted into the glass plate and that angle is denoted by R. Then lambda by 2, lambda is the wavelength of the incident light. In fact, if we check for delta is equal to 2 mu t cos R minus lambda by 2. This lambda by 2 term additionally comes because of the reflection at this point F. There is a rule: when light gets reflected from a denser to rarer medium, it will undergo a phase change of lambda by 2, phase change of pi, or we could say a path difference of lambda by 2. So simply you have to remember this equation. In thin films, when light ray is getting big, we get an interference pattern. The optical path difference is given by the equation delta equal to 2 mu t cos r minus lambda by 2. Mu is the refractive index of the medium of the thin film. T is the thickness of the thin film. R is the angle of refraction within the thin film. Lambda is the wavelength of the thin film. So we can actually derive and prove this equation. As of now, this is take it for granted that delta is equal to 2 mu t cos r minus lambda by 2. So we would use this equation when we study the Newton's rings in the next class. So as of now, let us remember that when we get an interference pattern from a thin film, the path difference delta is given by 2 mu t cos r minus lambda by 2. So that's about interference from thin film. Thank you.